as of now, I haven't done too much editing anyways. So editing a video isn't that hard, but I just haven't been able to do it. But I'll try to upload that video today and this video later this week. But I mean, let's just get into solving some problems. I think let's check which problem did we end up on. So we've done until 11. So let's check out problem 12 then. Sorry, actually I think problem 12 was something I just wanted to skip. Wait a minute. I think I did yeah, I did start with problem 12. And did I get stuck on part 4? Well, let's try it again with better luck. And also, I don't think I'll be able to cover all of the problems in this video, but for sure after the next video we'll move on to the next chapter and try to get the next chapters done maybe a bit quicker, so this project doesn't take forever. And now I have pre-solved these problems, so I think I'm able to give you more insight into these problems that way. But yeah, seems like also in my notes I've just skipped the rest of problem 12. So I'm sorry, but we'll move on to problem 13 now. And problem 13 is kind of interesting because especially at first it looks interesting because we get like formulas for the maximum and minimum of two numbers. And so here we get the examples of what maximum and minimum mean, but I'm sure you can figure it out yourself. And so we are given that the maximum, we have to prove that the maximum of x and y is equal to x plus y plus absolute value of y minus x over 2. And well, at first this formula looks interesting, but in my opinion in the end it's a bit disappointing because it's basically just putting the if inside the absolute value, because basically let's say that max of x and y is x, so x is greater than y, then y minus x is less than 0, meaning we put a minus sign in front of the absolute value signs when we remove the absolute value signs, and thus it becomes x plus y minus y plus x. The y's cancel out. Well, I'll show you. So if it's x, I'll move you a bit upwards, like that. X plus y plus absolute value of y minus x. Oh, expression is less than 0, so we put a minus sign in front when we remove the absolute value signs. And then of course y minus y cancels out. X plus x is 2x, leaving us with 2x over 2 equal to x. So, okay, that's smart, but yeah. And I suppose it's enough of a proof if I just do the two cases. First, if x is greater than y, and then x less than y. And it obviously works similarly for x less than y, which is 2x plus y plus y minus x over 2 inside absolute value signs. Well, now, because y is greater than x, this expression is greater than 0. Thus, we can just remove the absolute value signs, leaving us with 2y over 2 equal to y. So, at least to me, the formulas initially looked super interesting and kind of like, whoa, we actually could have a formula for something like the maximum of two numbers. But in the end, it's just a trick with the absolute values. But anyway, it's kind of nice still. And, well, the formula form in x and y is very similar. Now it's just minus instead of plus, for obvious reasons. And so I won't bother going through over that again. And then they ask us to derive a formula for max of x, y, and z. And the obvious way to do is to use the max formula twice. And I don't think it's interesting at all, so let's just hop over it and continue to number 14. And well, 14a, prove that absolute value of a is equal to absolute value of minus a. Okay, and we are told here the trick is not to become confused by too many cases. First, prove the statement for a greater than or equal to 0. Why is it then obvious for a less than or equal to 0? Okay, let's see. So, number 14a. So first case that let's first discuss the case a less greater than or equal to 0. Well, then absolute value of a is equal to a by the definition of the absolute value. And this is equal to minus of minus a, right? And then we can kind of do this trick that it's equal to, then this is equal to the absolute value of minus a, because if a is greater than or equal to 0, then minus a is less than or equal to 0. So a minus sign in front is equivalent to having absolute value signs around. So thus this logic is sound. And well, then Spivak asks is it then obvious for a less than or equal to 0? So, we prove the statement for a greater than or equal to 0. Why is it then obvious for negative a? Well, we can go kind of the other way. We can think of negative a as in one single thing, which is, in this case, less than or equal to 0. Same logic backwards until here, which is negative absolute value of negative a, if that makes sense. And so, by just going the chain of logic the other direction, we then clearly see that it's trivial also for a less than or equal to 0. I hope you understand my reasoning. Let's look at part B. Prove that if minus b, if a is between b and minus b, no, prove that a is between b and minus b if and only if absolute value of a is less than or equal to b. In particular, it follows that negative of absolute value a is less than or equal to a is less than or equal to absolute value of a. Okay. So, it's an if and only if, meaning we have to prove it in both directions. Let's first make the assumption that let's first assume the first and try to prove the second. So, assume minus b is less than or equal to a less than or equal to b. Okay. So, how do we approach this? Well, maybe I can have cases if a is greater than or equal to 0, then also b is greater than or equal to 0. And thus, absolute value of b is equal to b. And because a is less than or equal to b, which is equal to absolute value of b, first case is proven. Then, if a is less than or equal to 0, then also minus b is less than or equal to 0. Which means that b is greater than or equal to 0. Because again, absolute value of b is equal to b. And thus a less than or equal to b, and again we get the conclusion. Now I start to question myself. There's obviously also the case of b being negative. But no, there isn't, because then it wouldn't make sense, because if b was negative, then minus b would be positive, and this chain of inequalities just would never be true unless b is equal to 0. So thus we've proven the first direction of the if and only if premise, because as you know, if it's if and only if, it means that the first one implies the second one, and the second one implies the first one. So we would also need to fully prove this, we would also need to prove that absolute value of that, given that absolute value of a is less than or equal to b, then this would be true. But I feel like you already got the gist of how to prove this kind of things from the first one, so we can skip it. But what is this? In particular, it follows that absolute value of negative absolute value of a less than or equal to a, which is less than or equal to absolute value of a. Well, why does that follow from that? Oh yeah, I mean, I guess it comes from the same reasoning that b has to be positive. So then we can just add absolute value signs inside it, because it doesn't change it, right? That's how I would interpret this. What about 14c? Use this fact to give a new proof that absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. So the triangle inequality. Okay, let's try. 14c, absolute value of a plus b, and we somehow want to use this fact, I guess. obvious, that fact. Hmm. It is not obvious to me, so let's just try something. Well, a plus b, absolute value of a plus b is less than or equal to how could we use it? Well, I guess how we can do it is that because a is less than or equal to absolute value of a, then absolute value of a and b is less than or equal to absolute value of a plus absolute value of b, which is equal to absolute value of a plus absolute value of b, because these are both necessarily non-negative, and thus removing the absolute value signs, the outermost absolute value signs, doesn't change anything. Okay, I think this should be okay. But don't take my word for it. Okay, then number 15. Prove that if x and y are not both 0, then x squared plus xy plus y squared is greater than 0. So this reminds us a lot about this is very similar to the x squared plus 2xy plus y squared. But in this case, we don't have the 2, so it's not a perfect square. But somehow we of course just need to somehow get it into a square form. That's basically the way whenever you have to prove that something is greater than 0. So let's complete the square. And I mean we can write it this way. And let's even do brackets so it's clearer. X squared plus 2x times 1 over 2y. You'll see soon why I do it like this. Plus 1 over 2y squared plus 3 over 4y squared. If you want, you can confirm at home that this is indeed true. And well, this is equal to x plus 1 over 2y squared plus 3 over 4y squared. And obviously this is greater than 0, given that at least one of x and y is not 0. So just doing a pretty normal type of complete the square method gives us the desired result. Then this is a bit harder. 15, but the second one. We have to prove that this is greater than 0 with the hint that use problem 1. So let's go and see what problem 1 was about. In problem 1 we have a bunch of these kinds of things. And I think we need to use part V. Part 5, I mean. So let's first write the problem down. X to the 4th plus x cubed y plus x squared y squared plus x y cubed plus y to the 4th. And according to problem 5 part 1, this can be factorized in the following way. No, I mean, we can do a following kind of factorization. X to the 5th minus y to the 5th is equal to x minus y. Let me check one thing. Yeah. X minus y times this whole thing. So x to the 4th plus x to the cubed y solved this beforehand a week ago, and I had some genius idea, but I didn't write it properly down, so now I had to think again. Well. Oh yeah. Assuming that x and y are not equal, that case when x and y are equal is trivial, so we don't have to consider it now. So if we assume that x and y are not equal, then this is equal to x to the fifth minus y to the fifth. No, not equal to this. We can manipulate the equation in the following way. We just divide by x minus y, because we made the assumption that x is not equal to y. And we get the desired expression on the right hand side. Now we just need to show and because these are equal, if we show that this left hand side is positive, then of course the right hand side is of course always positive as well. And well, 5 is an odd number, and an odd number maintains the sign of the initial number, meaning that if x is greater than y, then the numerator is positive and the denominator is positive, so the whole expression is positive. Then again, if x is less than x is less than y, then x to the fifth minus y to the fifth is also less than 0, and thus the numerator is less than 0. That is negative, and also the denominator is negative, and thus the whole expression is positive. Meaning that in both cases, when x is greater than y and x is less than y, the expression is positive, and thus we have proven it. I was actually quite proud of myself when I came up with this method. It's very different from the first part of just completing the square, so it required some creativity. Now I'm just praising myself. Okay, what about sorry. What about 16 x plus y squared equal to x squared plus y squared only when x equal to 0 or y equal to 0? And I think this is quite easy. 16a. Okay, so we say that x plus y squared equal to x squared plus y squared. When is this true? First, let's expand the left hand side. X squared plus 2xy plus y squared is equal to x squared plus y squared. X squared cancels out, y squared cancels out. We are left with 2xy equal to 0, and thus x equal to 0 or y equal to 0. Quite simple. What about b? Now, second part. is equal to 0. We can divide by 3. X squared y plus xy squared is equal to 0. And let's factorize this. For example, let's take the factor y out. Y times x squared plus xy equal to 0. And thus y equal to 0 is one solution. Then we are left with x squared plus xy equal to 0. Again factor. And thus x equal to 0 is another solution. And then we are left with x plus y is equal to 0. So x equal to minus y. So we got 3 solutions. Y equal to 0, x equal to 0, or x equal to negative y, which is as desired. Let's move on to the next page, still continuing with problem 16. Using the fact that x squared plus 2xy plus y squared greater than 0. Show that 4x squared plus 6xy plus 4y squared is greater than 0. Okay. Well, that doesn't seem too hard. So, 16b. So let's start off with the fact that x squared plus 2xy plus y squared is greater than 0 if at least one of x and y is not 0. Then multiply by 3. We get that 3x squared plus 6xy plus 3y squared is greater than 0. And then let's just add x squared plus y squared. So we get that 4x squared plus 6xy plus 4y squared is greater than x squared plus y squared. And, well, this is the expression. This is the expression that we wanted. 4x squared plus 6xy plus 4y squared. And because this is greater than x squared plus y squared, which is obviously greater than 0, we have proved the premise. Or proved what we had to prove. And then C. Use part B to find out when x plus y to the fourth is equal to x to the fourth plus y to the fourth. Let's try. plus y to the fourth. When is it equal to x to the fourth plus y to the fourth? Maybe someone can already guess. Well, x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. Bum bum bum. Again, these cancel out with the things from the right hand side of the equality. From the equality. And we are left with 4x cubed y plus 6x squared y squared plus 4xy cubed equal to 0. And well, these numbers look strangely familiar. 464, 464. And if we take the common factor xy out, we have the exact same expression here as here. And thus, because on the right hand side we have 0, either xy equal to 0 or 4x squared plus 6y plus 4y squared equal to 0. But we just proved that this is greater than 0 unless x and y are both 0. So for this, the only solution is x equal to y equal to 0. And for this, the only solutions are x equal to 0 or y equal to 0. And thus, x plus y to the fourth is equal to x to the fourth plus y to the fourth if and only if x equal to 0 or y equal to 0. For some reason I find these problems quite satisfying because you kind of Michael Spivak very nicely guides the reader and the problem solver to the solutions, but in such a way that the problem solver, that is me and hopefully you, has a chance to still discover the main solution themselves while not getting too depressed. And seems like I have skipped number D in my notes at least. They are asking us to again do the same thing but 4 to the power of 5. And I'm pretty sure that wouldn't be too hard to do. Maybe a bit. It would just include a bit too much just writing things down. So I think we'll skip it for now. And I think we can already make a pretty good guess as to when x plus y to the power of n is equal to x to the n plus y to the n. It obviously depends on whether it's even or odd. So let's move on to problem 17. Problem 17. Find the smallest possible value of 2x squared minus 3x plus 4. And we even get a hint. Complete the square. Complete the square. So, okay. It's quite easy in my opinion. Let's open a new page. 17. It was 2x squared minus 3x plus 4. Well, this is equal to 2 times x squared minus 3 over 2x plus 4 which is equal to 2 times x squared sorry, and then we just do the square, so we get 2 times x minus 3 over 4 squared plus 4, and then we need to remember to subtract the 3 over 4 squared like this. And this is equal to 2 times x minus 3 over 4 squared plus, I think, is it 23 over 8? Or I'm not sure. Well, it's 4 minus 9 over 16. This is, well, 4 times 16 is 64. 64 minus 9 is 55. Is this the correct answer? I hope so. Well, we were asked to find the smallest possible value of this. And, well, because this part is always positive, then, or positive, non-negative, so thus this whole expression is minimized when x is equal to 3 over 4. So when this part is equal to 0, and thus the minimal value is 55 over 16. What about 17b? Find the smallest possible value of x squared minus 3x plus 2y squared plus 4y plus 2. So this is just the same thing as the first one, but we just complete the square for x and y separately. So it's x squared minus 3x plus 2y squared plus 4y plus 2 first x yields x minus 3 over 2x 3 over 3 squared minus 9 over 4, and then for y we get 2 times y plus 1, right, squared minus 2 plus 2, and so in if we group this a bit differently and cancel these 2's, we get this form. And because x and y are independent of each other, we can make this equal to 0 and this equal to 0. And when both of the squares are 0, we are left with negative 9 over 4. Quite simple. And, well, then there's 17c, which I find the smallest possible value of x squared plus 4xy plus 5y squared minus 4x minus 6y plus 7. And well, I have no idea how to do this because the x and y are not independent, because they are multiplied by each other. I know some partial what is it called? Like, you know, the multivariable calculus with like partial derivatives and similar. And I probably could be able to do this using some partial derivatives, but I don't think it's the intended way to solve it here. So if anyone has a solution for 17c in chapter 1, please let me know. I'm actually interested. It is a very daunting problem, and I tried to solve it for actually an hour and just couldn't do it. So please help. So that's it for problem 17, and that's it also for this video. I have other business to attend to, otherwise I would be making a longer video. But I hope you enjoyed and learned something new from this. I found these problems